Hello and welcome. You know, the world of artificial intelligence is moving so fast it can make your head spin. One minute you're hearing about machine learning, and the next it's all LLMs and AI agents. It can feel, well, a little overwhelming, so today we're going to cut through all that noise. We're going to build a clear, simple map of how AI actually works, from the moment it learns to the moment it starts to act on its own. You've heard all the terms, right? AI, machine learning, LLMs, and now AI agents. They get thrown around almost interchangeably in conversations, but here's the thing, they aren't the same at all. They're actually distinct layers in a really fascinating technological stack. So let's get to the bottom of it. What is the real difference?
That's exactly what we're going to do in this explainer. We're going to build that map together. We'll start with the most basic, foundational concepts, and then build our way up, layer by layer. And by the end, you'll see exactly how an AI learns, how it then learns to create, and finally, how it's beginning to act in the world.
To get started, we really need to understand the hierarchy of it all. The best way to think about it is like a family tree, where each new generation is a more specific, more specialized version of the one that came before it. Okay, so at the very top, the great-grandparent, if you will, is artificial intelligence. This is the whole entire field. It's any effort to make machines smart. Now, nestled inside that is machine learning, which is the most common way we do AI today. Its whole focus is on teaching computers to learn from data instead of being explicitly programmed. And then a really popular and powerful subset of that is deep learning, which uses these complex, multi-layered structures called neural networks, which, as you might have guessed, are inspired by the human brain itself. So we say learning, but what does that actually mean? How does it happen? Let's go ahead and pry open that infamous black box and take a look at the actual mechanics of deep learning. The heart of deep learning is the neural network. Just picture it. Data comes in through an input layer, then it gets processed through one or more hidden layers of these interconnected nodes, or neurons, and finally, a result pops out of the output layer. The really important part is that each connection between these neurons has a weight, which is just a number. And the whole process of training is just the model tweaking these numbers over and over again to get better at whatever its task is. Now, the magic of how AI learns really just boils down to two key areas of math. First up is linear algebra. It's what turns everything, text, images, sounds, you name it, into numbers arranged in grids called vectors and matrices. This is basically the language computers can understand. Then, to actually get smarter, the model uses calculus. Specifically, it uses derivatives to figure out which direction it needs to adjust all its internal connections to get just a little bit closer to the right answer. But how does a model even know if it's getting better? Well, it uses something called a loss function. You can think of this as its score. After every single prediction it makes, the model calculates its loss, which is just a number that represents how far off it was from the correct answer. The entire goal of training, the whole point, is to make this loss number as small as humanly or, machinely possible. Yeah, trying to minimize that loss is a lot like trying to find the lowest point in a huge valley while you're blindfolded. After you take a step, the loss function is like the feeling in your feet. It tells you if you've just stepped uphill, meaning a worse prediction, or downhill, which is a better one. You just keep adjusting your next step based on that feedback, always trying to go down. This methodical process of finding that lowest possible loss, well, that's called gradient descent. So for years we had these neural networks, and they were getting better. But the recent explosion in AI capabilities, the one we're all seeing now, it wasn't just about making bigger networks. It was sparked by a brand new, totally different design. And this breakthrough architecture is called the transformer. You see, before transformers, models like RNNs had a big problem. They read text one word at a time in sequence, and they'd often forget the beginning of a long sentence by the time they reached the end. Transformers completely changed the game because they process all the words at once, and their key innovation is this incredible mechanism called self-attention. It lets the model look at every single word in a sentence and see how it relates to every other word, no matter how far apart they are. That right there is what gives modern AI its deep, nuanced understanding of context. So if you take one thing away from this section, let it be this. A large language model, or an LLM, is the product you interact with. It's like the car. But the transformer, that's the powerful, game-changing engine inside that makes the whole thing go. The architecture is what made all of this possible. This incredibly powerful new architecture didn't just give AI the ability to understand, it gave it the ability to create.
And that leap brings us right into the amazing world of generative AI.
And the difference here is really fundamental. For decades, most AI was what we call discriminative. It learned to classify things. Is this email spam or not spam? Is this a picture of a cat or a dog? Generative AI does the exact opposite. It doesn't just recognize a cat, it can generate a brand new, totally unique image of a cat that has never, ever existed before. Now, within generative AI, there are a few key approaches. You've got GANs, or generative adversarial networks. These are really cool. They use a two-part system where a generator creates images and a discriminator tries to tell if they're real or fake. This competition forces the generator to get incredibly good. Then you have diffusion models, which power a lot of the image tools we see today. They start with just a canvas of random noise and then methodically, step by step, refine it into a clear image. And finally, there are VAEs, or variational autoencoders. Think of them like an artist that learns to compress data into its most essential features, its idea, and then uses that compressed concept to generate all sorts of new variations. Okay, so we've seen AI that learns and AI that creates. But the next frontier, where things are headed right now, is AI that acts. This is where we move from a passive tool to an autonomous system. And this is what we call agentic AI. So what really separates an AI agent from a plain old chatbot? Well, a chatbot has that LLM brain we talked about. An agent has that same brain, but it adds these critical components around it. It has memory, so it can learn from past interactions. It has access to tools, like APIs, so it can actually take action in the digital world. And, most importantly, it has a control loop. This lets it make a plan, try something, see what happens, and then adjust its plan. And it keeps doing that until a complex goal is achieved. It doesn't just answer a question like, what's the weather? It can pursue a goal like, plan and book my entire vacation. All right, now that we have our map all laid out, let's see how these concepts actually play out in the real world. This is where developers and companies have to make some pretty crucial decisions about how to put this technology to work.
One of the biggest decisions right now is whether to use a proprietary model, like the ones from OpenAI, or an open source model. Proprietary models are often incredibly powerful and pretty easy to use through a paid API, but you have very limited control over them. They're a black box. On the other hand, open source models give you complete control and transparency. You can modify them and even run them on your own servers, which is a huge plus for data security. But they do require more technical expertise to manage.
Now, a really key technique for making these models more reliable is called retrieval augmented generation, or RAG. You see, sometimes base models can hallucinate, which is a nice way of saying they just make stuff up. RAG helps prevent this. Before the AI generates a response, the system first retrieves relevant, factual information from a trusted source, like your company's internal documents or the live web. It then augments your prompt with this factual context. It's basically like giving the AI an open book test. It grounds its answers in reality. And believe me, this technology is already having a massive impact. We're talking about everything from designing new protein structures that could lead to life-saving drugs, to writing and debugging software code, to creating entire 3D worlds from just a couple of photos. Generative AI is rapidly becoming an indispensable tool across science, engineering, and of course the creative arts.
So there you have it. We've mapped the world of AI all the way from the simple act of learning, to understanding, to creating, and now to acting. All the components are in place for systems that can pursue complex goals with more and more autonomy. So this really just leaves us with one final question to think about. Now that you understand the pieces, what's the one task you'd give it next?
Like and subscribe for SimplifyTech, explaining one concept at a time, simplifying the technology and AI.